Hey! So you're looking for a little extra help. Momentum, impulse, how to solve, how this even works. Yes, let's get right to it. Let's get in the zone with what to do. So the two things we're really doing with momentum and impulse, right? The first is we're doing... The first thing we're going to do is conservation of momentum, right? Cons of mom, there are none. And that's a good old P before equals P after. And the other thing we did quite frequently was something called the impulse momentum theorem. And this was affectionately called FATMAV. This is right. J, which is impulse. Now, we're doing one of those with most of these problems. If it's a collision or an explosion or anything of this sorts. Now, how do I know the difference between the two, and how do I know which one to do? Right? That's yikes. The big clear difference is similar to what we talked about energy. If I care about everything in my system, all of the objects, so if I have 2, 3, 4 objects, whatever it is, if I care about all of them, that's when I'm really going to look to do a conservation of momentum. When, however, I'm talking about a single object in the grand scheme of things, that's when we are going to default to FATMAV and the like. So what I have here is one question worded two different ways, and let's try to figure out whether or not we can work through this with both of these methods. So let's look at this. Now this question might be a little familiar, but enough for us. So a 0.5 kilogram block is moving 20 meters per second on a smooth frictionless surface towards a stationary sphere with 2 kilograms, and they give us a graph. Now, reminder with graphs, what we do with them as any and all graphs, the first thing we do is read, the second thing we do is slope, and the third thing we do is area. And looking at this graph, reading it would give me forces and times, maybe. Sloping it would give me force divided by time. I don't think that sounds very good. But area would give me force multiplied by time, and I know that impulse is fat. It's fat, bro. So that's probably what I'm going to do here. So it says block strikes at T0 on the graph, and then the plot of the graph is there. Great. And the first question they want me to do is, what's the impulse? Well, for this, we sort of already figured this out. I'm going to be doing area. Now, I'll look here for this. Change colors. It looks to me like I have shape 1, 2, and 3 here, right? Which looks like 2 triangles and a box. Now, important thing to watch out for this is that this time is actually in milliseconds, and these forces are in the thousands. And if I do this, this impulse here, if you do the area calculations, the change in momentum for this is going to be 10 Newton seconds by finding those 3 areas and adding them together. And now let's head further into our questions and see what else we're going to do, which of our 2 methods we're going to use to approach this. It says, what is the speed of the ball? Last time I checked, ball was one of the things, not all the things. So because ball is one of the things and not all the things, I'm going to be using FATMAV. Now here I'm only going to use MAV. And the reason is I already know what change in momentum is. So if I were to do this, we were trying to find this. So I'll divide both sides by M. So delta P over M would be delta V. And delta V, these are always final minus initial. And now for this, it had said that the ball was initially at rest, so bye-bye, right? So what I'm left with is that the final velocity will be equal to the change in momentum divided by the mass. Change in momentum we just said was 10 Newton seconds, divided by the mass, which of the ball is 2 kilograms. They call it a sphere. 2 kilograms, 10 divided by 2, 5 meters per second. Okay. You also notice a little note here. Remember, velocities are a vector, so this value ended up positive, which means in the diagram it would be moving in that direction, which it should be. Okay, let's keep going. So again, just to recap, I used, fat mav, right, as a method to solve here because I was talking about a single object. Let's keep going. What is the velocity of the cube? Last time I checked, the cube is one of the objects, not all of the objects. So again, I'm going to be using the same concept here. Now, I'm going to be using delta P, right, is M delta V. But this is going to be a little different. And the main difference here for me in this problem is that delta P. If we think about this, right, for our diagram, right, when these two, so I can just draw this, that'll be easier. If we think about not drawing with the highlighter,
silly me.
So I will just have the ground, right? I'll have my cube, which I'll draw as a box, and I have my sphere. When they're being hit, right, when they're actually in contact, the cube is pushing the sphere that way. Because of something called Newton's third law, the sphere is actually pushing back on the cube that way. So if we were to think about this, remember with momentum, everything's a vector, so we care about directions. That means this impulse, negative, has to be negative for the cube, because the cube is going to be slowed down, it's being pushed backwards. So it's important for us to keep that in mind as we work through this. So again, I'll divide both sides by m, so change momentum over mass is equal to delta v. This would be equal to vf minus initial velocity. Now, here I know the initial velocity, and I'm trying to find the final velocity. So if I algebraically rearrange this a little bit, I'm going to get the delta p over m, right, and then plus the initial velocity is going to be equal to the final velocity, remembering that the impulse has to be negative. So for the cube, right, this is going to be negative 10 Newton seconds divided by the mass of the cube, which was half kilogram. So this is 0.5 kg plus the initial 20 meters per second, and this will give me my final velocity. 10 divided by a half is actually multiplied by 2, so this is really negative 20 meters per second plus 20 meters per second. Jeez. Final velocity then is actually going to be equal to 0. Whoa! Whoa! Crazy. Awesome. So we know that in this example, the cube does stop. A little complicated. Now, for the last question that was on this problem, it asked whether or not this is an elastic collision. I'm not going to do all the calculations, but we will sort of set this up. For it to be an elastic collision, the kinetic energy in the beginning has to be equal to the kinetic energy in the end. The problem is we don't know if that's true. So the first thing would be to find the kinetic energy in the beginning, and this would actually be the kinetic energy of the cube. And then find the kinetic energy in the end. So this would be the kinetic energy of the sphere or the ball. And I'm going to find those two values and then make a comparison between them. And by doing that comparison, I can see if they're equal, it's elastic. If the initial kinetic energy is bigger, then it would be an inelastic collision. Remember, inelastic collisions, mechanical energy is not conserved. All right, let's keep on rolling. So here's the same diagram. Slightly different question as it's asked. So again, half a kilogram block slides 20 meters per second smooth surface and strikes a sphere with 2 kilograms. After the collision, which is totally spelled correctly, so I don't agree to that anymore, the block comes to rest. Now you notice this question we're given different information. So in the original one, I was given questions about the graph, right? And I gave a graph and this, and we want to know how fast would the ball be moving after the collision. Now, for a problem like this, I don't know about the objects individually, but I certainly do know about them as a system. So we're going to try this with a little p before equals p after. So I have momentum of the cube initially, plus momentum of the ball initially, and then it's got to be equal to momentum of the cube in the end, and then momentum of the ball in the end. Now, I know from reading this problem that the ball is initially not moving, right? I know that in the end, the cube is also not moving, so I'm really left with the cube in the beginning. That momentum has to be equal to the ball in the end. So if I try to set this up now, and I'm looking for how fast the ball is moving, this is mass of the cube, initial velocity of the cube, mass of the ball, final velocity of the ball, which is what I'm looking for. So I'll divide both sides by mb, divide by mb, cancel out. The cube, we said, was half a kilogram, multiplied by that 20 meters per second that it's moving, divided by, I know that this is 2 kilogram for the ball, and this will be equal to, sorry about that, to the ball's final velocity. So a half of 20 is 10. 10 divided by 2 is 5 meters per second, is how fast the ball is moving. And because this is positive, we know it's moving this way, which has to be in the diagram. Okay, and you can see we got 5, and if we scroll back up to our other answer, we did in fact get 5. So no matter how you do these problems, you will be getting the same answer if you have enough information to solve them. Key indication, I think, is if it's asking about one singular object and you know impulse, you have it given a graph, right? But if we don't, we tend to default a lot to the P before P after, especially when you can see this problem's a lot more vague. So when we have that vague question, it's a little bit more like this. But if we have a lot more detailed information, or we have that graph, remember, watch out for those graphs, we're going to be defaulting to using a lot more P before P after when we don't know as much as the information. Hope this is helpful, and if not, please reach out as always, through email, whatever you need to do. And thanks for watching. Until next time.